Thank you. Yeah, welcome, ladies and gentlemen. At first, I would like, before I start my presentation, to say thank you twice. Thank you on the one hand to the organizers of this very interesting and exciting conference, and thank you to you that you are still here also attending the last session in this conference, and you still have the power and willing to do so. I would like to present today on the topic of testing renewable power plants on high voltage right-through capability. So actually HVRT was already mentioned several times today. And in this regard, I would like to specify in particular grid code requirements and testing procedures, as well as also corresponding testing systems. My name is Julian Langstettler, and I'm the division manager at FGH. And as you may not know FGH so far, I would just give you a very short outline of it. FGH is more or less a German medium-sized company, and it consists of 3 different entities. FGH Research Association was already founded in 1921, so it's quite old, and it was always focused on research and development in terms of power system analysis and systems engineering. We also have a certification office. In fact, it was the worldwide first accredited certification office for the assessment of the electrical characteristics of decentralized power generators. And we certify, that means we assess the electrical characteristics of wind turbines, solar power converters, also entire wind farms or solar power plants, as well as also components and storage systems. So actually what was also mentioned today by my colleague, Mr. Bala from DNV. And on the other hand, we have an engineering office, or let's say engineering company, where we provide software development, but we also provide, in particular, engineering services in the field of grid integration of renewables. We have more than 25 years of experience in this field, and we do also provide engineering for FRT testing systems. In the past, we manufactured them by ourselves. We don't do it today anymore. We have a cooperation partner for it, but we still do the design for it. So coming back to my presentation, and in this regard, I would like to emphasize on specific testing equipment also for HVRT. I would like to start with a short introduction, and motivation for HVRT. I will also emphasize on grid codes, and in particular also the possibility how to test HVRT capability. I will also show you some experience from prototype testing, and in the end I will conclude with some statements. So what is actually the current situation of fault right-through? So as we already have heard several times today, an LVRT capability is absolutely mandatory for power generating units in grid codes whenever there's a significant share of renewables within the system, and the renewables are more or less system relevant, whenever their disconnection would otherwise threaten the grid stability. And so far that is state of the art today, and also incorporated in the IEC standard. And FGH already developed the testing equipment and procedures already in 2003, and our procedures were also later on incorporated in the IEC standard for the for wind turbine 61400-21 for power quality. However, since this is state of the art, we have to tackle new challenges today, and they definitely also come up. And they increase with the further penetration of the dispersed power generators. And in this regard, we also talk about temporary overvoltage and high voltage systems. New grid code requirements are evolving. And in this regard, also Germany set up new requirements already in 2015. And I'm going to highlight them later on again. However, at first, I would like to give you a short outline of what is actually the relevance of overvoltage in the system, how does it happen, and what is the relevance of HVRT. So overvoltage may occur in the system due to, on the one hand, maybe line capacities for long transmission lines that are combined with load shedding or also generator tripping. Or on the other hand, after a fault recovery, when a system failure occurred and the fault was cleared, directly after fault clearance, when you have a very short peak in the voltage after recovery. However, these two phenomena, they differ in terms of time duration. So we on the one hand talk about milliseconds, whereas for the load shedding and the unloaded transmission lines, we talk about minutes. And they also differ in terms of location and system propagation. So that means one are only regional phenomena that do not have a wide impact on the system itself. However, load shedding and also generator tripping may affect a huge range of the system. And whenever I talked about LVRT, I always show a scenario which was calculated in Germany in 2001, which actually happened also in 2006 with a major incident. And we also had an incident, a major one in Germany in 2012 in the grid of the system operator 50 Hertz, which was also introduced on Wednesday. That is more or less a system which is in the northeastern part of Germany, which is characterized by high penetration of renewables, whereas the load is very small, comparable. And in this system, there was a short circuit, a two-phase fault on a transmission line in the extra high voltage system. And the voltage dip expanded over the system itself. And you see here that even the wind farms, so the offshore wind farm here on the Baltic Sea, that they were affected with a voltage sag of almost 60%, whereas at the fault location we had in the 110 kV system, we even had voltages down to 48%. However, in this system also, a lot of wind turbines are already erected that are not LVRT compliant. So during this period, it was in winter period, there was a lot of wind, and most of the wind turbines were operating. And in this regard, after the fault occurred, a significant amount of the wind turbines, they tripped. However, after the tripping, because of open unloaded transmission lines, we had a very strong voltage boost in the system itself. And this led to further tripping of wind turbines. And in the end, we had the problem that almost 1.7 gigawatts of installed wind power capacity was disconnected at that time. And it may not seem much for Indian standards, but for this grid section in Germany, this is a very significant amount. And if there was the requirement for HVRT, it would have been a better effect in this regard. So you see here also the overvoltage that happened in the high voltage system. So whenever such incident occurs, you will try to avoid that it will ever occur again. So the result of such incidents is always that there is afterwards a requirement found in the grid code, and it is highly discussed, of course. So actually the result is that there's a HVRT requirement, and the capability is required in the recent grid codes. And we expect that there's also a similar evolution for HVRT requirements that we've seen for LVRT. And in this regard, I would like to highlight also the German requirement from the new revision of the high voltage grid code that was introduced in 2015 in Germany, where we have an LVRT and an HVRT requirement. And the HVRT requirement says that you have to withstand voltage swells up to 130% of nominal voltage for a period of 100 milliseconds, and in addition, also 125% of nominal voltage until 60 seconds. So this is basically the HVRT capability, so that means that you are able to fault right through. However, we have an additional requirement that during the fault itself, the wind turbine or also the solar power plant must stabilize the system in its disturbance. So that means you have to inject a reactive current. And when we talk about overvoltage, you want to decrease the voltage and lower the voltage impact. So that means that you shall behave like an underexcited synchronous generator. So that means we are in the figure here in this area. However, HVRT requirement is not only introduced in Germany, we have seen it already today. It was introduced also in Italy, in South Africa, in Australia, and Canada. and it is discussed and proposed also in the US. I've learned this morning that it was already introduced in last year. I'm happy to hear that. And also in Denmark and India, it's currently in the discussion. So focusing on India again, so far the CEA introduced the LVRT requirement in the connection standards for wind power plants in 2013, and there is a time fixed where wind turbines commissioned after this fixed date must be LVRT compliant, which is in 2014. And this compliance shall be tested and verified by a third party and shall also be part of the type certification. However, in the recent amendment of the CEA, where the grid codes is always clarified for connectivity of wind turbines, there was also an HVRT requirement introduced for wind and solar power plants, which was also mentioned today. And I've shown here, just taken from the draft version, the voltage against time profile, where you see that even voltages up to 140% of nominal voltage here in India are supposed to be fault right through capable. So when you've got such requirements in the grid codes, you must have a procedure how to test them. And in order to have a procedure, you also need equipment how to test them. And FGH developed a setup which is quite similar to the LVRT setup. And it is based on the Ferranti effect, where you have overvoltage with capacitive charging. And this is actually also what happens in the grid when the overvoltage occurs. Here you can see an equivalent diagram of a transmission line, where in the horizontal path you have the inductance and the resistance, whereas in the vertical path you have capacitors. And when there's a short circuit, you will have a connection here at the end, and only the inductance is visible. So that means you've got, for the LVRT equipment or testing procedure, you have got an inductive voltage divider. However, if there is an unloaded transmission line, you at the end have only the vertical path, which is affecting the voltage itself, so only mainly the capacitor that's having an impact. And this is shown also in the HVRT setup system, where the short circuit with the inductance will only be replaced by capacitor with a damping resistance. So actually the serial impedance is still the same, and you can use it redundantly. So that means you have on the one hand, you have the possibility to manufacture HVRT standalone test systems, but you can also combine them within an LVRT or HVRT test system. So far, our maximum design was 170% of nominal voltage for overvoltages, rated at 33 kilovolts and up to rated powers of 8 megawatt. And here you can see some examples of such testing systems. The one that we've built for pilot testing in 2012, which we did together with the wind turbine manufacturer in Germany, with Enercon, where we had that prototype only rated for 2 megawatts for LVRT, including also the switchgear, whereas here there's the HVRT add-on system. And here you can see a commercial full-scale system, which is integrated in 3 40-feet shipping containers, so it's quite a huge system. One container is containing all the switch gears and the circuit breakers. The other one is containing all the inductances for the serial or for the short circuit inductances, and one container full of capacitors and resistors. So from the pilot project testing, we made more than 100 tests up to voltage swells up to 140% of nominal voltage. And we've seen of course, some results that we've seen also in the field testing that we also simulated before. One is that you must make sure that you also meet the specific ramp rates of the IEC standard. So that means, according to the IEC standard, which is currently only a draft version, but it will be published next year, you will have to have a specific voltage level within the testing, for the testing voltage, within 20 milliseconds. And this is quite fast, and you may have to have an adaptation of the switching sequence in order to cope with this requirement. On the other hand, you also see here in the picture on the right that the transformer, which is normally used, of course, for solar power plants, but also for the wind power plants, where the direct conversion of electricity of the generating unit is on low voltage side. However, the testing will always be done on medium voltage side, so there will always be a machine transformer in between. And this machine transformer has a saturation, of course. And this saturation on secondary sides limit the overvoltage that comes from primary side. So whenever you have 170%, for example, on primary side, it doesn't mean that on the device under test you will also see this 170%. It's maybe only restricted to 125%. And this shall also be taken into account by the developments of grid codes. Yeah, as you can also see in the lower right picture, it's also very important that you have a damping resistance within the circuit itself, because otherwise you have the amplification of maybe harmonics or even interferences with the ripple control, so that must be nicely harmonized. You can see also, because of the requirement that I introduced in Germany, where you also have to inject a reactive current, that this specific wind turbine here from the pilot testing, that it was also due to the voltage swell, that it also replied with an appropriate reactive current injection within the tolerances of the German grid code. So at this stage I would like to conclude. HVRT is definitely a crucial capability and subject to grid codes, and we've talked about this today. It's really, really crucial to introduce such requirements at a very early stage, because retrofitting, you have the experience here in India currently, retrofitting of already existing turbines is quite expensive. And the sooner you introduce such capability and requirements, the better it is later when you want to meet also your 175 gigawatts of renewable energies here in China, here in India. Sorry. So we already heard that also compliance testing and verification is needed, and HVRT test systems and procedures are already available and successfully in performance. We have a few of them already manufactured, and they are successful in operation. We stick to the capacitive overvoltage configuration since it's based on real grid effects. There are also other concepts where you use transformers. However, we do think that the system effects are better simulated with capacitive overvoltage. And an appropriate setup is also important for the prevention of grid repercussions. So that means actually no resonance with harmonics or something else. Okay, for the grid code requirements, you should definitely also take saturation effects into account. So don't come up with a requirement that says you must withstand voltages up to 170% of nominal voltage. It actually doesn't make sense, at least for the generators. There's always a transformer in between. Yeah, and there's definitely also subject to investigation for wind turbines in terms of control strategies. In particular, when you introduce such kind of requirement, it needs a long time also for manufacturers to go along with it. And this should also be taken into account. So far, that was my presentation on HVRT. Thank you for your attention. If you have any questions, please feel free to ask.
Yeah, any questions, please?
Hello, my name is Falk, company SMA. I would like to ask you whether it is, from your perspective, feasible to have not your medium voltage equipment as a test environment, but in a voltage source inverter. Should be much cheaper, easy to handle, and it reflects more precise the real grid impedance in that case.
Would it be also on medium voltage level, or would it be a low voltage test setup?
would be a low voltage test
Yeah,
setup.
okay. Yeah, we do always, so you could also easily do the same setup here on low voltage side with the inductive voltage divider. But you usually talk about these high currents, or let's say the high current that must be managed, and also for usually the fault comes out of the system. So it is basically coming from medium voltage side, directly interconnected to the device under test. And I haven't seen yet any, let's say, shootout between a test setup that was using a converter solution compared to real grid data. I haven't seen it so far. What I've shown for the inductive voltage divider, this is definitely the phenomena that also occurs within the system itself. What you only do is you reduce the short circuit power at the point of common coupling because of the serial inductance. However, it is only a different range when you test then. It doesn't mean that you're outside a limit or boundary where you say, okay, this is a condition which does not take place in the real world anymore. That's not true, because that's the reason why you have specific ratios within the testing guideline, that this is definitely maintained, that it is shown a real case then. And so far I have heard from projects where this is definitely subject to investigation, but I haven't seen any proof of concept for that.
The power range of the present installation is 2.75 megawatt, and under investigation is 4 megawatt.
Okay.
Yeah.
So what is the limitation of your FRT container?
8 megawatts,
8
depending on the
megawatts,
voltage.
Yeah,
Yeah,
but
but it's fine for solar power converters, sure.
Which converters in parallel,
Yeah.
of course.
Yeah, sure,
Yeah.
it can be scaled up.
Another reason is maybe also that you have the interaction with the system itself. I'm not sure whether this is done properly with a converter solution. This is more or less an island. And if there is some interaction with the system itself, and we often see that also within measurement campaigns, effects that are not directly also describable, I'm not sure whether you can emulate them also with the converter.
So it's quite common used for like inverter, PV inverters, and
Yeah,
like for inverters which are actually like attaching to the grid as PLL, so it's okay. But if you look towards synchronous generators, I also have my doubts that this works fine, because you don't have the loop, the feedback loop, what the synchronous generator like feeding into the grid then has an impact on the grid. So that's what we have at least seen in our
Exactly.
measurements and so on.
Yeah,
But-
maybe it has to be a case-by-case investigation.
Sure, sure.
But it's-
My question was actually also with regard to the rating, because you said 8 megawatts, and because of like weak grids, typically you can't go further. What about the high voltage ride-through container? What is the impact? The impact on the grid? You have what you have proposed, and secondly, what's the power rating? So how far can you go up?
Maximum power rating was also shown on one of the slides. It was for rated voltages up to 36 kilovolts. You have maximum rated powers of 8 megawatts. Could easily do also 10, but then the size of the equipment gets increasingly complicated, and it's very expensive, but it would be possible. And the other part was...
So the question with regard to the HVRT, if I got
Yeah,
your
the
diagram right,
repercussion.
you're actually
Yeah.
disconnecting during this phase, do you? Where you just feed from the condenser, or did I get it wrong?
No, it's basically both. Yeah, you still have the serial impedance still online, so that means this will also limit the effect of the overvoltage that you see at the device under test to the system, and it's similar to LVRT testing where you have a short impact on the system, or a small one. However, it is absolutely smoothened due to the serial impedance, but it's still there is some repercussion. So you shouldn't test at a very, very weak grid connection point then.
Thank you very much.
Thank you.
Any other pressing question? Then we move on. Thank you very much again.